voice lasts? Let's find out. So, don't forget about the final. The final is 1 week from today, right? In this classroom. We'll take it right at the start of 3, and yeah, look at the final info page. I will release this final once I have to take it. I've made it, and I have to take it to make sure there's no little bugs in it, and then I'll release it so that you can see it too. But it won't be available to take until next time, of course. But yeah, I just want to finish up these final review slides, and I think that's all I got. So we were talking about hypothesis testing. We have questions, and we know how to formulate a null hypothesis, an alternative hypothesis, and do some simulations to figure out p-values to tell us which way is the right way. Should we reject our null hypothesis? Should we fail to reject our null hypothesis? Let's next talk about bootstrapping, and then we'll do a confidence interval after bootstrapping. So, okay, back to Titanic this time. Let's do a Titanic example. Let's calculate a confidence interval for the average passenger age. All right, so the ages of these passengers. Let's pretend that like we're on a lifeboat. We've only got a few of the Titanic passengers. Let's bootstrap to kind of get a better picture of the makeup of the Titanic. Let's see, I gotta run this. So we do have we have the census of the Titanic, but let's pretend we didn't. And so Titanic, table, read table, Titanic, and I want to know the ages of passengers. So some of these passengers, unfortunately, we don't know their name. Like Mr. James Moran, he had no number associated with his age. Nan stands for not a number. And so we kind of want to exclude those people because we can't do math on Nan. It's like we didn't know the age. So let's do like a dot where the age values are like 0 or above, like a normal number that will like kick out all those Nans there. Where the age values are above or equal to, let's say, 0. And so now he's not there, and only people with real ages are in this list, in this table. And all right, so let's pretend we were on like a lifeboat and we only had the contents of the lifeboat to like figure out how old were people on the Titanic. Like we didn't have the full passenger list. So let's pretend. And we can check. We can always check against the real answer because we know the real answer. But let's pretend we only have a size 100 sample of passengers, and that's all. Not the 714 or whatever, but just 100. And then we'll show that bootstrapping gives us a good confidence interval, even though we didn't have the full data. That proves that it's a good idea. So let's take a sample, say Titanic.sample. Give me 100 people, and don't clone anybody, so without replacement. So here's my sample of 100 people. And if I go to the sample and I ask for the ages of everybody, so go to the age column and do a mean, I get that. Little over 29 years old is the average age of this sample of 100 people on the Titanic. It's not the full people, it's like the people in the lifeboat. We're not sure. All right. But I'd like to know, all right, this is my one good sample, the people on the lifeboat or whatever. I'd like to know what was the average passenger age for everyone on the Titanic, not just the 100 in my sample, like the whole population. So pretending we didn't actually know that, we can use bootstrapping, right? We can use bootstrapping to get at a good idea. Like we have our original sample. The whole idea of bootstrapping is we have our original sample, all these values, and what bootstrapping does is it clones some of them. It makes another sample that looks very similar, yet different. Like sometimes it clones people. Like it'll clone that person twice. Maybe it'll skip that second person, get that guy. Maybe this guy gets cloned, that guy gets skipped. And so we get another sample that looks similar, but yet slightly different. And we can calculate the average age of this sample, right? And just by virtue of cloning some people and kicking out other people, it might just randomly look it's another good sample, right? It's another sample that's kind of indicative of the population and yet slightly different from the original. And so that gives us more ideas about what was really true about the underlying population. And so the goal is, like, we do all these bootstrap samples. Like, we calculate the average age of this one, average age of this one. Just do a million of those. And then we got a bunch of average ages, and we kind of graph them. Right? We kind of graph them, and we see, here's the original average age. But we've got all these bootstrap samples. Average age is this one, this one, this one, this one, this one, this one. And we just find, like, what's the range that 95% of those bootstrap average ages were in. 95% of them. And then we say that's probably most likely 95% of the time what the average age was. It's between those two ends for the total passengers on the actual Titanic. So let's do that. So remember what bootstrapping is. It's just we're generating a new sample from our original sample. It's a resample. Sorry, I'm probably going to cough a lot today. Okay, so I want to generate a bootstrap sample from our original sample and give back the average age, because that's what I'm trying to calculate for every new resample. Like, what's the average age for this one? Because maybe that's a better picture of the population. If you do this enough, you get a really good idea of what the population average age could be. So I want to generate one bootstrap sample in this kind of way, make a sample, figure out the average age. So give me back one bootstrap average to make a function for it. So get a new sample from our original sample. So it's a resample. Take your original sample, which is just called sample for us, and sample from it with replacement. So clone some people, kick out other people, but take the same size. That's perfect. So by default, remember what that's doing is it's with replacement and it's getting the exact same number of things. So by default, just say dot sample without anything means you take the same size as the original sample. So give me back as many rows and do it with replacement, which is perfect. That's what bootstrapping is. And then what we want to do with that resample is the same thing. Give me the average age of that one, because it'll look a little bit different. And that might be closer to what the real Titanic was. And so it'll kind of average away all the differences of this one good sample that we took, and it might look a bit more like the real Titanic. So if we do this enough times, we can have a good picture of the population average age. This time it was a little bit less than our sample's average age. So it cloned some younger people, kicked out some older people. All right, so if we do this enough, times, we're going to get a bunch of bootstrapped average ages, and taking confidence intervals from that will give us a good picture of where we think the real average age for the actual Titanic was. All right, I'll generate averages from, let's do 5,000 bootstrap samples. And so I like to make my little repetitions variable. Let's do 5,000 times. I want to save all these averages, so I'll make an array, right? I'll do bootstrap means, starts out as an empty array, and then 5,000 times I would like to call one bootstrap average, right? Get me another answer, and then append it to that array, saving that back in. Excuse me. Thank you. So yeah, we got that. And if I run this, it might take a second. It's a size 100 table it's got a sample from. We will have in this bootstrap means array a bunch of different means. Bootstrap, 5,000 of them to be precise. And they're all different from the original, usually. Some of them are like, the average age is old. The average age is much younger than we thought from the original sample. And we're not sure. Like, pretend we don't know the true Titanic average ages, but this is going to give us a better picture as to what it could have been. So if I make a histogram of this, we can see the spread. It will center around the sample's age, the original sample's age. There it is. But you see it goes on either side. And so what we want is, all right, what are the average ages? What's the range for 95% of these things? Because if we get that back, that will tell us with 95% confidence, right, where the range that the true population of the Titanic's average age was. Might be somewhere within there. 95% of the time it's supposed to be, at least. So now I got all these values. I guess we'll keep them there. And yeah, to get a 95% confidence interval, I want to like center around 95% of the data to get a 95% confidence interval for the average age. And that's going to be a couple percentiles, right? So 95%, what's the middle of that? It's like, there's 5 on each, there's 5 left over, so you want to go 2.5 on each side, right? So the 2.5th percentile of the bootstrap means all the way to the 97.5th percentile. And so this is telling us, all right, for our sample, we are 95% confident that the true average age of Titanic passengers was between this and this. If you were to do the thing again, 95% of the time we have it there. So because we took a sample of an actual population, we can figure out the real average age of the Titanic passengers. And let's see, 95% of the time it's going to be within there. So I guess if I teach this class enough semesters, 1 year, it won't be within this range maybe. But here's the real answer. Actual average age for every passenger. And it looks like it's smack dab in the middle there. So that's perfect. And so that's what bootstrapping can do for you. It can give you another window into your sample. It can give you another sample without, like, for free, without having to go get another one. Okay? That's the beauty of bootstrapping. Any questions about that? And from that, you can calculate a bunch of different answers to see, like, the spread of what something that you're not sure about for the population might be, like the average or a median. And then you're in business. And this just goes to show that it really does work. Because you usually don't know the true thing, but we've done this enough as an example to show that, yeah, it really is if we do know the true thing, it will find it. So we have some confidence in it. Yeah, so that's confidence intervals and bootstrapping. Be confident on that. All right. Next, let's do regression. So regression is predicting, right? Predicting numerical things. Usually we're going to do it with a linear regression, right? We're going to calculate the best fit line through data. So let's do father and son example. That was always, that had some good correlation. Let's do that for regression. So it's the son's heights data. And then, sorry to the mothers in this column, but it was more correlated between father and son. So just select out only those. And then let me include, by the magic of copying and pasting, all the necessary functions for all this. So we'll need all these ideas. Let's go over them quickly. Just standard units, right, is going to convert an array of data into standard units, which is distances or z-scores or distances away from the mean in terms of chunks of a standard deviation, right? How many standard deviations away from the mean is all this data? That's putting it into standard units. Correlation, right, is a number between -1 and +1. How linearly correlated is this data? The lowercase r is the variable we use to represent that, right? 0 means no correlation, it's all wonky, but like 1 means positively correlated, They go, when one goes up, the other goes up perfectly. -1 means perfectly negatively correlated. So when one value goes up, the other goes down, right? And then you can calculate the best fit line through the data. So here's the slope, the intercept, and then this is the best fit answer. So like you give me a bunch of x values, and I'll predict for you all the y values. So yeah, let's use those now. So let's first notice that this data set is linearly correlated. So let's go to a scatter plot. So sun's heights. Let's do a scatter of father and son. And then we could be like, oh yeah, when one increases, the other increases. Looks like there's some positive correlation there. You can also ask the scatter plot to draw a best fit line. Fit line equals true. Okay, seems decent. And then what's the real correlation? We can use that function. How did I not run this? Correlation for the sun heights table for father and son. And that's about 0.5. So that's decent, right? That's a decent linearly correlated thing. And now let's use this best fit line to make a prediction for like somebody who's not there, right? The way that we calculate this line is we can use our slope and our intercept to get the y equals the mx, right? The m and then the b. So we could get the slope, we get the intercept of the best fit line to this one exactly, and we could use that to calculate the predicted height. So you give me the father's height, I'll give you our prediction. I'll read it off the line of the height of the son for that father that has not yet grown up or something. So let's do that. So m is slope for this table, father and son, using father to predict son. Father is the x, son is the y. And then b is intercept. Yeah. And then, just for fun, because we got the sun's heights table going, right? Let's see how good we were for each of these. Like, for each of these father's heights, we have the actual sun's height. Let's use our best fit line to do the prediction for that sun's height based on the father's height. So, predictions is, all right, you give me mx plus b, right? Sun's heights, dot column, father, that's the x. So multiply mx plus b. That's going to be a prediction for every sun's height. Does that make sense? So like for the first one, for the father's height, reading it off the line, it looks like we're predicting the sun's height to be a little bit taller than it actually ended up being. And that happens, right? It's never perfect. So those are our predictions, and we can add that back into the heights table. Maybe I'll call that suns or heights with predictions. And so I'm just reading off the line. And this is exactly this, make the predictions. Those are your fitted values. So that's exactly, I could have used this fitted values function. It did exactly that. But this is more educational. So cool, we got that now. And then we could see like how far off we were, right? It's never perfect. Because you know that the height of somebody has to do with like nutrition and like their grandparents' heights too. Like it's not just the dad, but the dad is a good predictor. And so now we got all these things. So for like height 65, we're predicting that the son's height, or the father's height is 65 inches. We'll predict the son's height is a little over 68 inches. So will be taller. And you see that is kind of a good approximation of everybody that we had for 65-inch fathers, right? That's pretty decent. That's a nice line through the data. Does that make enough sense so far? So what we've done, we calculated correlation. We drew the regression line manually just now. Are you ready to calculate the error, root mean square error? Because that's what the best fit line is defined in terms of, right? The reason we have like this is the best line is it's because that is the best line through this data that minimizes the root mean square error among everybody in the original data set. So that's important. To calculate just errors in general, it's always actual value minus your predicted value. So you're either too high, too low. So let's calculate the errors for our data. So we know, right, the original height, it's the sun, just call them sun. And then we have our predicted height, so that's actual minus predicted, right? So those are all the errors. Like, okay, the first one's off by negative amounts, and sometimes it's positive. Let's add that back into the table too. Yeah. So it looks like we predicted too high. So the error was, all right, from our prediction, we need to go down to get the right answer. From this prediction, we also need to go down a little bit. From this prediction, looks like the sun was a lot taller than we thought they would be on that line. And so we need to go up from our guess, okay? And so these are our errors. To calculate, like, what's the average error? The number is root mean square error, all right? So what you do, the way that you calculate it, because you gotta like get rid of the negatives. The point of this being the best fit line is like all of the errors, they average together to be 0, right? The positives outweigh the negatives. That's like we're like right in the smack in the middle of everybody, and so it makes no sense to like do just like the average error right now. Does that make sense? I hope so. Like np.mean on errors, it is legitimately 0 if you round it. It's just off by very tiny amounts because of Python and arithmetic, but it's really just 0 because the positive errors outweigh they match the negative errors. So if we want to know like the total amount of error, well, we need to do like either an absolute value or a squaring, and everybody likes to square instead. So root mean square error, how to calculate error, like the average error of your predictor, is you read it backwards, right? So root mean square means, okay, square the errors first, take the average of the squared errors, and then do the square root to bring it back to the original units, because otherwise you squared it. Now you're in the squared units, like meters squared. Now we're back to meters. So yeah, let's do that. So let's do errors squared first, right? Square them. Take the average, np.mean, right? Mean square error. That's just by itself. That is the thing. RMSE is the full one. MSE is mean square error. And then RMSE is MSE, just square root of it. That's the last thing. So it looks like we are about 2.2 inches off in our prediction each time on average. That's the root mean square error of our predictor, which is honestly not bad. It's like, okay, you give me the height of a father. We don't know the height of their son yet, but our prediction for that unknown son's height will be only off by like a couple inches. That's pretty neat on average. That's pretty cool. So yeah, I hope that makes sense. And this was like the best slope for this was our m value, right? And the best intercept was b. So it looks like the slope was 0.5. The intercept was almost 36 inches. These were the regression estimates for slope and height, slope and intercept. Right? Now I want to show you, I just want to prove to you like the best fit line is defined in terms of this root mean square error. Are we ready for that? Questions about any of this first? Because like you give me, maybe this isn't the best fit line through the day. You give me a line, you give me your best guess of the slope, you give me your best guess of the intercept. I can find for you, I can do the prediction, right? I can find the error of that prediction using that line to make predictions. And then I can get the root mean square error of that. So let's make a function that does that. This is how the best fit line is defined. Like you give me your idea of the best fit line through the state. You give me a slope, you give me an intercept, and I can make predictions, right? The x's are father's heights. The original y's are the son's heights. And then our predictions based on those x values are, all right, use your guess. Use your line. mx plus b. And then your errors are, okay, you know the original y's, right? So errors is y minus your actual minus your predicted values. So, all right, you think that this isn't the best fit line through the data. Here's another line. You give me another another m and another b, and I'll use that to make predictions, and I'll calculate those errors, and I'll calculate that root mean square error. That's root mean square error is, all right, error squared, do it backwards, right? Square, then root, or then mean, sorry, and then root to that. There's the root mean square error of your predictor, your m and your b. If you think you can do better, give them to me, and I'll calculate the root mean square error of that. And this, if we minimize this function now, right? You say minimize, you say RMSC, minimize the inputs to this function, or give me the inputs to this function that could give me the lowest answer for root mean square error, because that's what it's returning. Then I have to say smooth equals true to have it do it right. But look at how it finds that, all right, the smallest root mean square error I could possibly find comes from you giving me an m value of this and a b value of that for those inputs. And those are exactly equal. Exactly equal to what we solved for there. So that just goes to show that, all right, if root mean square error is something you care about and you would want to, right? That's something normal to want to minimize. It's a good definition of average error, kind of. Then our best fit line calculation, our best fit line formulas for the slope and for the intercept, those do give you the best answer if it's a straight line that you're trying to solve for, which is very nice. All right. That's pretty cool. So like somebody did the hard work for us already. This is the best slope and intercept through your data if you think that it's a line that's predicting it. But you could also use this minimize function to predict to use it to find the best quadratic curve through the data, the best, I don't know, any higher polynomial as well, like any function. You can minimize that if you think you have a better guess and it's not like a line. Calculate the root mean square error of making predictions for your wonky looking function. That works too. But yeah, root mean square error minimization gives us the best fit line, which is great. And I think the last thing I want to do for this slide is let's do a bootstrap, right? Because we know that this data set on fathers and sons heights does not cover everyone ever. So it's probably not perfectly accurate, but we can, and so this slope through the data, this intercept through the data, is probably not the actual slope for the best fit line through all of humanity's data. So we should want to make an interval rather than just have one answer, right? We should want to make a confidence interval. So let's do some bootstraps to figure out what is a good interval, confidence interval for 95% of the time, the right value for the slope of the population of every sun's height ever. Okay, so same idea. We're not sure that this is the true answer, so let's make a bunch of bootstrap samples, resamples. I'll do 2,500. All right, so I want to create 2,500 bootstrap samples. Find the slopes this time. Save all those. Because then I could do my percentiles to get, okay, this is a range for the slope of the best fit line through all father and son height data ever. So let's save that. What do I want to do? I want to make a bootstrap sample over my, the son's heights. The whole table itself is a sample of father and son's heights, right, of humans. So just take a bootstrap sample just by calling out sample. Let's get the slope of that bootstrap sample, so I'll call it bootstrap slope. And that's my slope function. So on that sample table, using the father's height to predict the son's heights, that's what the function was calling for. And then that's a new slope. So slopes equals np.append to the existing slopes array, that new bootstrap slope that we found. So I'm just getting a new but similar, right, sample, a resample of my original sample. So that's maybe more representative of the human population of father and son's heights. And then I've got all that sitting in this slopes array now. And if I want to, I can get a confidence interval. So let's do 95% again. We know the endpoints of that, right? So we want to find the endpoints of the 95% confidence interval for the true slope through the data of all father and son heights ever. The left end would be the 2.5th percentile. The right end would be the 97.5th percentile. With a comment, we'll print them both out. So it looks like, honestly, it could be anywhere. So like, all right, the father's height goes up an inch. The son's height then will go up 0.4 inches in the lowest to maybe 0.6 inches in the highest. And so that's a decently wide range. You draw that. So we're not super confident, probably because our table only has like 150 things in it. You had more son's heights, you'd be more confident, right? You'd have a tighter interval. That's just what that does, right? It'll be less, let's see. It'll be less random and fluctuating because you have more things to rein it in if there's more samples. So yeah, that's fun to think about as well, though. So you can bootstrap not just like averages, you can bootstrap slopes, bootstrap whatever you want. Any statistic you care about, and that will help you generate a confidence interval for the thing at hand. That's fun. So regression, linear regression specifically, we're predicting numerical values. So for example, son's height from father's height. We good with that one? You just shout out if you have questions, all right? Let's see here. Dun, dun, dun. I think, yeah, the next thing I want to do is, yeah, classification. If we're ready for it. Yeah. Let's do that, and then I think, yeah, we don't have to do the fancier ones, but that's fine. Let's make that happen, because that's the main stuff, and I'll give you more time to study. So, okay, let's do the breast cancer example again, because that was a good one. So let me read that in, and then we'll talk about it. And then one of these columns was like the patient ID because we don't want to say their name. That would be a HIPAA violation. This ID has nothing to do with whether or not they had breast cancer. It's just like a random number, just like your student ID is. It doesn't really tie anything interesting about you back to you. So we'll drop that column because we don't want to train ourselves on predicting IDs or like seeing how far apart IDs were. That doesn't mean anything. Everybody else is important. All right, so for this table, we've got a bunch of results, numerical results about a breast cancer examination. And so we've got information about different things having to do with that examination. And then the class column is 1 if they ended up having, I guess, a certain kind of breast cancer, and 0 if they did not end up having it. And so that's maybe this is like biopsy results or something. So this is the kind of information that we have in our table. And we have this many patients, 683 of them, with some of them had the cancer, some of them didn't. And so what we would like to do is you give me, like without having to consult the doctor, right? Because it's the doctor deciding all these classes. Just quickly, you give me the results of an examination, all these other numbers, right? Clump thickness, uniformity of cell size, whatever these things mean. Give me those numbers, and we will calculate our best guess of what the class should be. All right, that's what it means to train a classifier. So regression was predicting numerical stuff. Classification is predicting categorical stuff. Did they have cancer? Did they not have cancer? All right. And so our goal is to train a let's do a 5 NN classifier, because generally the idea is it's a KNN algorithm, right? That's the classification algorithm that we learned, k nearest neighbors. And so we fix a number called k, and we'll fix that number at 5. We'll say that 5 is our good number. That's the k that we've chosen. It should be an odd number. And what it means to make a prediction then is, let's say here's your data. What's my this? What do I want to do with this? Yeah, let me draw some dots, I guess. Dots, 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 dots. So like this is your data set. Because all of your data, right, all these numbers, you can plot them. Pretend that this is like a coordinate in like a 10-dimensional data set. So pretend this is a 10-dimensional space I'm plotting dots in instead of 2 dimensions. So here's my dots. And then, so those are all the blue class things. Then here's some green class things. Whee. Usually they would be more separated, but that's okay. And so, let's say you come along and, I don't know, you have a new person that got their, that had an examination done, and their data puts them here. So here's your new person, yeah? There's your new person. And so the idea of k nearest neighbors is you find that many things nearby your new point that you're not sure what the class of it is. We're not sure if that one's going to be green or blue. We want to find our best guess. We want to classify it, right? We want to classify it. So we're going to find the 5 nearest things to this dot. It's like here's one, right? This may not be to scale. There's 2, there's 3, there's 4. Debatable where the 5th closest thing is right now. I could see either one of those being the 5th closest. Let's say it's this one. I don't know. Let's say those are the 5 closest things. And then what you do is you start counting the classes of those things that you knew, right? Because this is it's going to be from your training set. We'll talk about that in a second. But we're going to count, all right, what are the classes of each of these? Okay, I see 4 greens and one blue. And you're going to let majority rule. So from the things that I knew nearby this point that I'm not sure about, I see that there's 4 things in the green class and 1 thing in the blue class. And so if I had to guess for this new point, I will think that it's going to be green. Right? So our prediction then for this guy is going to be predict green. Does that make sense? Just on paper? Because that's all it is. That's all k nearest neighbors, the algorithm is. You fix your k value, you go find that many things nearby this new point that you're trying to classify, look at their classes, and take a majority vote. It's also very important that you use a odd k, right? Because you could have 2 and 2 if you had k equals 4 or something, then you don't know what to pick. So that's k nearest neighbors in a nutshell. To find the distance, first of all, also, to find the distance between points, remember that what you can do is, it's essentially the Pythagorean theorem, just fancy, and it generalizes to multiple dimensions. But like you got 2 points, x1, y1, x2, y2. You got to do this to every point, right? From every point in your data set to this new point. Like you got these 2 points, you want to know how far apart they are? The way that you do that is you find their differences of their x values. x1 minus x2 squared. The order didn't matter. It could have been x2 minus x1 squared because you square it. Then you add that to y1 minus y2 squared. And then you take the square root. And this formula works regardless of how many dimensions. You just keep on adding. If there are more things like z1, z2, you do the same pattern, right? As long as you need to. And so that's how you find the distance between 2 points in any dimension. You just keep on, if you go back to the original slide, we talked about that, okay? So that's how you find the distance, and then we just do a bunch of table stuff, a bunch of table operations to like find the 5 nearest thing. You do some sorting, right, by the distance. You add the new column in. We talked about all that before. So yeah, on paper, hopefully, k nearest neighbors makes sense. Any questions about that before we go to code? This is definitely the most complicated, probably, algorithm in the class, but it's the coolest, for sure the coolest. And then also, to make sure that your classifier was a good classifier as you build it, you want to split up your data set. So first you shuffle it so that nothing's in any conceivable or like recognizable order. Like this is your data set. What you do is you shuffle it first, like now it's been shuffled, pretend, and then you cut it off, right? You save away some pieces of it that you're never going to look at again, right? Because this is labeled data. So you separate it into a training set and a test set. And the training set is the stuff you use the actual labels on, like you use that to train your classifier. And then to make sure that your classifier didn't just memorize everything in the training set, you've hidden away some things that you haven't seen, it hasn't seen yet. That's your test set, right? And what you do is you feed in the data for your test set into the classifier based on the training data, and you have it predict, and you saved away the actual class of this guy. Maybe it's green or something. You have it predict for using the training set for the class of this thing. Don't tell it what it really was. And then make sure like it gave you back green. Yeah? Make sure it said that one was green. Make sure it says this one is blue. Like you try it for everybody, right? Have them all, test them all out. And then you compare and make sure, right, it did the right thing for a good amount of them. Otherwise, that means you overfit. That means your classifier just memorized the training set, and that's not good. So that's why you save some things in your test set, because that can then give you like a score for how good your classifier was on things that it hasn't seen yet. Because that's the goal, right? Give your classifier like a new person. We're not actually sure what their class is. We're not sure if they have cancer. That's the whole point. We want to help out the doctors. So that's going to be the first step. We need to split this data set up into a training and a test set. But then we could like plug in our distance algorithm, like add new columns to our table, sort by the things, the distances to get the k nearest things, take a majority vote. Like the rest is Python, all right? But the paper idea is the most important thing that I want to get across to you, at least today in this review. Does that make enough sense? All right, so let's create a training and a test set for this data set. So we got 683 things. Let's just chop it in half. I think that would be the easiest. So 683 over 2 is unfortunately not even. You can't have half a patient. So what we'll do, first we got to shuffle it anyway. So shuffle patients. So give a new order. So because there probably is some discernible order. Like maybe they're cancer first, then not cancer second or something. Let's fix that. So it's patients dot sample, as many of them as there are, with replacement equals false, so that we don't clone anybody. Keep the same amount, just give me them in a different order, please. All right, and then we'll make a training set. Let's make the training set a little bit larger. So let's have 342 things in the training set. All right, equals from the shuffle patients. Take up to that many. So take the first 342 things, which means indices 0 to 341. There's my training set, and then the test set is everybody after that. So start at index 342, and then go to the end. The last index is 682, which means 683 is the thing you give there to go up to that, but not including it, right? So yeah, there's my split up data. And so we're going to train based on our training set. And if you run this on your own end, because you're going to make a different shuffling, you might get a different accuracy amount. All right. So yeah, let me copy and paste all the important code for that in. So here's all the code that we wrote for classification. And let me try to explain it all. So we got our distance function. What that's doing, right? It's subtracting. It's doing exactly that. Subtract the x's, the y's separately from each other, right? Subtract each of those corresponding coordinates, which is perfect if you give those to me in an array, because if you do array subtraction, subtract the corresponding elements, which are the same coordinates, right? Just the x's, just the y's subtracted from each other. Then you square them all, right? Square them, square them, square them. And then you sum all those things up. You add. And then you take the square root. That's the outside thing. So that's perfect. That's a distance calculation for any dimensional space, any dimensional point. That's perfect. Lovely. Technically, this also works for 0 dimensions. It just becomes the absolute value. Because you square one thing, and then you take the square root, just gives you back the original number, but positive. Okay, so there's that. And then this all distances function. You give me the training set. You give me some row that we want to calculate all the distances from the training set to that new row, right? And so everything but the class are your attributes. So just like this table, right? We don't want to do any math distance calculations based on class values because we don't know the class of the things we're trying to test for, right? So get rid of that. That's not part of the attributes. Our attributes that we're doing training with is everything except for the class. All these guys. We chop that up. We chop that off because we don't get that for this new point that we're trying to classify, right? We don't know its class. That's the whole point. So our attributes are everything but that. So we drop that. And then we find the distance from that new row to everybody, right? From that new row to any row that you could possibly give. So we apply this little inner function, right, to our attributes. Apply that distance. And so that's going to give us the distances for each element in our training set to this new point that we care about classifying. And then our goal is to like attach that into a table. It's like here we are calling that here in this nearest function. So this nearest function, it's going to give back a table of the top k things, right? You give me a training set, you give me the k, you give me the new point that you want to classify. We'll find the k nearest things to that point in the training set. Okay, so the first thing we do is find the distances to that new point, that new row. And then we attach that to the training data as a distance column. And then we sort by those distances, right? Because we want it in ascending order. Give me the smallest things first. Taking the first k things gives me the k smallest things, right? The k smallest things as a table, including their distances. And so that's what is returned in this nearest function. And that kind of feeds into KNN, right? KNN is the function we would like to call eventually. You give me the training set, you give me some new thing we would like to classify, you give me the k. Go find the k nearest things, and then go figure out the class label that is the majority, right? Go take a majority vote. See if it's 1 or 0. That's this majority function. You give me the table, go to the class column, count the number of 1s and count the number of 0s, because all that you have in this table is the nearest things, the k nearest things already. That's guaranteed to be odd if you did it right, right? And then it's like if there are more 1s than 0s, the class that we're predicting, the majority class is 1, otherwise it was 0, because we're assuming it was always odd. It must be less than otherwise. So that's perfect. And then that will give you your prediction. KNN will make the prediction for you. And if you wanted to evaluate how good your predictor was on your test set, that's what this evaluate accuracy function is doing. What it's doing is, all right, you give me the training set, you give me the test set, the entire test set, and you give me the k, because the k changes how good it is, right? K equals 1 is probably not that good. K equals 5 is probably significantly more accurate, because it's not going to be, like, misled. At least as easily. So you got those. And so, yeah, again, the attributes of the test set, drop the class, pretend we don't know about it for a second, because we want to evaluate without giving any hints, right? So we want to do k nearest neighbors on the training set for each row of the test set with that k value. So that's what this little inner function is doing. So we apply that, and this is the predicted class then for every point in our test set. Test attributes to apply this function. That will give me the prediction, like 1 for the first thing, 0 for the second thing, 1 for the third thing. It'll keep on going and give me the predicted class for each element of our data set, of our test set, using the training set to do the classification. And then we compare against, because we saved away, we really do have the class in the test set, we dropped it for a second, we'll compare against it now. So here's our predicted classes for the test set, and then the actual class column of the test set, we remembered what it really was, we know what it really was, go see how often we got it right. So check for equality, see how often that was true, and then you can make a proportion, right? You can do a percentage calculation by dividing by how many things were actually in the test set, all right? So that's kind of like the short idea of all of those functions that we talked about in detail last time. I don't know, unexpected indentation. It must have been me doing that. There we go. But yeah, any questions about these functions? Did I jog your memory of them? You want me to re-explain anything? Just shout out. Because our goal now is, let's do a 5 nearest neighbors. We just want to call evaluate accuracy. So like do that. Because we called it training set and test set. So evaluate with the training being our training set, the test part being our test set, and K, we want it to be 5. And it looks like, if you do this, it'll take a second because got to try everybody in the test set. We get a 97.4% accurate classifier, and that's pretty darn good. And that's great. Like, you give me these data values, even for a point I've never seen before, because we saved some away in the test set, we can do pretty good, very accurately. We can be very accurate about guessing, or not guessing, it's predicting, right? Classifying whether or not that data from that examination indicates cancer. At least this specific kind of breast cancer, which is very, very powerful and very, very cool, right? Should make you feel good that we have this kind of ability. And yeah, it just gets better from here. If you take more data science classes or machine learning classes, you'd probably find ways to make this even more accurate. And that's great. Okay. Let's see here. I guess the last thing I want to say is, the last thing I want to say about doing classification is, remember, for your data sets, patience. Remember that sometimes when you're doing, when you have a data set and you're doing classification, it's going to do all these distance calculations, right? And so it really depends on the units of all of your data, whether or not the distance calculation is going to be useful. Because it looks like all this data, like all the numbers are between 1 and 10, that's perfect. You want everybody to be on an even playing field. But say like this column was like not between 1 and 10, it was more between like 20 and 10,000, like that was the range. That's such a huge value, it's going to overshadow everybody else when you do a distance calculation, right? So to get everybody on an even playing field, if you had that kind of, like some columns had different units and those values took on giant values, that would cause the distance calculation to like prefer those distances between those giant values and like forget about everybody else. You want everybody to have equal weight. And to do that, the easiest way is just to turn everybody into standard units, right? So remember, just type this in a very long comment. If the range of values for your columns are widely different from one another, I don't know, for example, one column ranges from 1 to 10, and another ranges from like 1,000 to 9,999, then it's going to forget about the smaller column. Let me just show that to you. We have a distance function, right? Distance, make array, 1, 2, 2, 3, 4. Like those are all small distances. But if you had this, right, like 1, 2,000, 1, 4,000, the distance is going to be just the distance between these guys. This 1 and this 3 didn't really matter. It's like, what if this became a 4? 1 and 4, oh no. It barely changed the answer. See that? It was really preferring to compare these guys. So that the 3 to 4 didn't do anything at all. So that's the point I'm trying to make here. I hope that makes sense, right? So then it's a good idea to turn these all into standard units. To get every column on an even playing field by converting them to standard units. And another name for standard units is z-scores, right? They like the statisticians. They really like their abbreviations. They really like their variable names. So if you don't do that, your distance calculations will be biased. just like I'm trying to say here. Like this 1, 2,000, 3, 4,000 was this distance apart. This 1, 2,004. Let's make it 5. Changing 3 to 5. It was practically the same distance because this one just took so much weight, right? The values were so widely apart that this small distance didn't really make a change. When the values are close to one another, then it does something. Like if I change it to 5 here, then you see like, okay, there was a decent jump. Well, this one barely did anything. And that's what I'm trying to say here. So turning everybody into standard units kind of, you just use the standard units function. Standard units, what did it take? Just took the array. So instead of the original column for patients, let's move this down here. I don't know why I can't scroll past that. I'd like to put this down here, please. Oh, gotta do it one at a time then. There we go. So like here's the original column 1 or column 0. If I change it to standard units, then every value is going to be between like -3 and 3 because usually they're normally distributed. Like -4 and 4 for sure, even if they aren't then. But like everybody, all of your values will start looking like this. Some value between like -3 and 3 usually. And then their weights are going to be the same. Then the distance calculation won't matter. Won't make a fuss if there's different columns because all those ranges are going to be the same. Okay. And I think that's more or less what I wanted to say about that. So just be careful. For this data set, it didn't really matter because all the ranges of these values were between like 1 and 10. And that's perfect. And nobody's going to be nobody's going to be more important than anybody else. But hopefully you can see that if you had some wildly different units, then it really, really helps. That it's really going to change the answer for your distances if you change everybody to standard units. Z-scores, turn them into distances away in terms of standard deviations away from the mean. Cool. And so that's classification in a nutshell. Any questions about that idea? All right, I think that's all the code that I wanted to write. Got more examples, but I think I'll just get one more. That's the meat of it. I do have some other things, but that's just extra. So yeah, let's have this be the last one. Dun, dun, dun. So this is the last chapter of the book. This is updating predictions based on new data. This is all about Bayes' rule, right? Bayes' rule is this. If you want to know the probability of something given something else, this little pipe character, it means given. Given that I know that something else has happened. How does that change the probability, the prior probability from before I knew about this new thing? So read that as given. And this is the formula. Probability of A given B is equal to the probability of B given A. So it's like something to put on your cheat sheet. Times probability of A over probability of B. And you can calculate this in this way. So let's say, again, our lecture example, where we know that, okay, in the lecture hall, there are 60% of the students are second-year students, they're sophomores, 40% of the students are juniors. And among the second-year students, they're kind of half and half. Half of those guys have declared a major, half of them have not declared their major yet. And then among the third-year students, they've grown up and they know what they're going to do with their lives. So among the third-year students, 80% of them have declared their major by now, only 20% are undeclared. And so let's say you randomly pick a student in the classroom, like the professor randomly picks a student, and they ask them, hey, have you declared your major? And they say yes. Now what's the probability that that student was a second year? There were more second years, but does this new knowledge, given this new knowledge, does that change the probability of that randomly picked student having been a second year? That's the idea. So given some new knowledge, given that I know that that student has declared their major, now what's the probability? Now what's the probability that they were a second year student, because it's not just 0.6 anymore. Does that make sense? Okay. So the idea is here's the answer, it becomes the probability of the flip, right? Declared a major given that they were a second year. We declared a major given that they were a second year. times the probability of them being a second year, just a random student being a second year, over the probability of anybody having declared their major. So some of these you can read off. This idea, this is the flip one, right? There's a 50% chance that a second year has declared their major. So if you know that somebody, given that they're a second year, the probability that they've declared their major is 0.5. Right, so that's the other way around. That's not what we want. We want the other way. We want the flip of that. So the probability of that a student has declared their major, given that we know that they're second year, it's like, all right, second year, what's the probability they've declared their major? 0.5. Okay, so that's that one. That's 0.5 for that. What's the probability that just somebody in general is a second year student? That's this one right here. That's just this, 0.6. Probability of being a second year is called the prior probability before we know anything new. 0.6. And then this is the probability of being declared at all. What's the proportion of the class that has declared their major at all? That's these guys, right? You're either here or here. If you add those up, that's the probability of being declared at all. And so the way to get those, the way to figure out what was this percentage, what was this percentage, is you can start multiplying to do something and something. So what was the probability that there was a second year student and they were declared? Well, just take the original probability of the second year student being a second year student times the probability that they declared their major. Hopefully that makes sense, right? Because it's 60%, then half of those 60% declare their majors, that's 30, right? Which is 0.6 times 0.5. This is 0.6 times 0.5. That's the probability that a second year student has declared their major. And then the probability that a third year student has declared their major is 0.4 times 0.8, right? And these two taken together are the probability that anybody at all has declared their major. So this over here now is equal to that sum of 0.6 times 0.5 plus 0.4 times 0.8, because they don't overlap. Yeah. And so if you do that math, we could do it together. Just at the very end here, we'll do, I don't know, Bayes' rule. We've got 0.6 times 0.5, or let's do the whole thing. 0.5 times 0.6 divided by this guy, 0.6 times 0.5 plus 0.4 times 0.8. So one of them is going to be your numerator, right? Plus 0.4 times 0.8. And with that, we get about 48%. Which just immediately is not the same as the probability of just being a second year, right? This new knowledge has changed the way the world is, right? So it's a little less than chance that randomly picked student was a second year, given that we knew that student had declared their major, because there were more third year students that declared their major, even though there's fewer of them in the class. Interesting to think about. And so that means the probability of being a third year, given that we know that they declared their major, is the opposite of that, because that's whatever was left, right? So it's more likely that they were a third year student than a second year, because that was the other option, right? That would be your 52%. And that, I believe, is what I wanted to explain about Bayes' rule. So you're just updating your prediction. Given new knowledge, you just use this formula, right? Because usually one of these, the other way you could just read it off, right? This way was declared given that they were second year. So given that we knew this person was a second year student, what was the chance that they declared their major? That's on the table itself, on the probability table. And we wanted the flip of that, and then this formula gives you the one in terms of the other, if you can find everybody else. Okay? And I think that'll do it. That's the last chapter of the book. Any questions about any of that? Because yeah, I had just other little examples, but they just in case we got through this very quickly. But we've already been over an hour, so I'm good. I'm good with stopping here. Yeah, any last questions about any of these topics? So I'll give you all this code, and we plenty of time to ask me questions and study in the rest of the time. But yeah, if you're good, I think that's all I got. So we made it to the end. Don't forget, like, this review slide is not comprehensive, right? Definitely go back to the chapters, go reread any of them. That the whole point of these review slides is to like hint at to you like the things that you're a little fuzzy on still. It's like, all right, if classification still seemed fuzzy, then you want to go back, right? If the example today didn't make too much sense, then you want to go back to the chapter, go back to the original lectures and the assignments on that. All right. And then there's also stuff we didn't talk about, just like a lot of probability. That's totally fair game for the test and stuff. We did a little bit at the end, but there's plenty more where that came from. So don't forget that that all exists, but just trying to give you the best bang for your buck. So yeah, I think we made it. Any questions about these examples before I finish up? All right. Yeah, so the final, of course, don't forget about it. Don't forget about the extra credit assignment if you want to, but the final will be on Wednesday in class, starting at class time. We only get 2 hours, and then we have to be kicked out probably because there's another class coming in after us, so definitely make sure to be on time if you want the full time. And yeah, I think that's all that I've got. We got the last few assignments due soon. Let me know if you have any questions. I'll still have office hours this week. My office hours next week will change a little bit. I'll give you some announcements about that soon. And yeah, thanks for putting up with me for the semester, guys. I'll see you one last time on Wednesday. But the rest of the time today is all yours now to work and to ask questions and study.